Thank you, everybody. Welcome to my presentation. My name is Yan Chen. I'm now a professor at the University of Winnipeg, Canada. The talk I'm going to present today is about a polynomial time algorithm to solve the so-called two-mass sort problem. Here is the outline of this talk. First, the motivation of this work. For this, I show you what is satisfiability problem, as well as what is the two-mass sort problem. Both of these two problems are NP complete. Then I will present our algorithm to solve the two-mass sort problem in polynomial time. For this, the following important and interesting concepts and techniques will be discussed in greater detail. They are P-graphs, P-star graphs, tri-leg graphs, then by searching a tri-leg graph, bottom-up will generate its layout representation. By using this layout representation, we can find the solution to the two-mass sort problem very efficiently. Then I will analyze the time complexity of this algorithm. Finally, I will conclude with a brief summary of this talk. First, the motivation of this work. For this, I show you the satisfiability problem. For this problem, we are given a logical formula in the conjunctive normal form like this, where each Ci is a clause which contains a set of literals. The problem is to find a truth assignment for all the variables, such that each Ci evaluates to true. This problem is NP complete. The maximum satisfiability problem is an optimization version of satisfiability that seeks a truth assignment to maximize the number of satisfied clauses. This problem is NP hard. The two-mass sort problem is a simplified version of the mass sort problem with each Ci containing at most two literals. Although this problem is a simplified version of the mass sort problem, this problem proves to be NP complete. The main idea of our algorithm is to transform the two-mass sort problem to another problem, which can be solved in polynomial time. For this, we consider a logical formula in the conjunctive normal form like this, with each Ci containing at most two literals. Then we define another logical formula, but in the disjunctive normal form like this. Well, each di1 is equal to Ci1 and Xi, and the di2 is equal to Ci2 and minus Xi. Well, each Xi is a newly introduced variable. Then we can prove C has at least n star satisfied clauses if and only if D has at least n star satisfied conjunctions. Then we have a new problem to find a truth assignment might maximizes the number of satisfied conjunctions in this logical formula. Well, each di is a conjunction. Then we can prove that if we can solve the above problem in polynomial time, then we can also solve the two mass-solved problem in polynomial time. As an example, let's have a look at this simple logical formula, but in the disjunctive normal form. If we set C1 to 1, C2 equal to 0, C3 equal to 1 to 0, C4 equal to 1, C5 equal to 1, and C6 to 1. Then we have a subset of three conjunctions, D1, D3, and D5 satisfied. In fact, they are a maximum subset of satisfied conjunctions. To find such a maximum subset of conjunctions satisfied by a certain truth assignment, we'll introduce a new notation like this, which is said to be J or minus J. Then you can see such a notation always evaluates to true. Our purpose is to insert this notation into each conjunction to represent any missing variable. In this way, we'll rewrite the above logical formula in a new format. But this new logical formula will have the same value as the previous one. But doing this enables us to represent each conjunction as a variable sequence like this, with each negative letters being removed. Now we can compute the appearance frequencies of variables in variable sequences like this. Then we can impose a global ordering of variables such that the most frequent variable appears first. For example, for the above variable sequences, we can impose the global ordering of variables like this, where variable C5 appears first. It is because the appearance frequency of this variable is the highest. Then we can sort all the variable sequence according to this globally imposed ordering of variables. But here, a start symbol and an end symbol are used for technique convenience. Now we are able to construct a graph structure called P-graph for each conjunction like this. In this P graph, we have a path going through every variable in the corresponding conjunction. In addition, for each star notation, we'll have a spine like this. For example, for this star notation, we have a spine like this. For this star notation, we have a spine like this. For this star notation, we have this spine. We can also represent each spine by the subpath covered by it. For example, for this spine corresponding to this star notation can be represented by a subpath which going through 3 nodes, B2, B3, and B4. For each P graph, we can define another graph, the so-called P graph. For defining this graph structure, special attention should be paid to the overlapped spines. In this P graph, we can see this spine is overlapped with this spine, and this spine is overlapped with this spine. But you should notice that this spine is connected to this spine, but not overlapped. From this, we can see that the union of 2 overlapped spines make a new but bigger spine which covers 2 consecutive star notations. Then, the overlapped spines exhibit some kind of transitivity. Our purpose is to generate the transitive closure of all the overlapped spines. Then we can define what is P-star graph. It is the main path of the corresponding P graph plus the transitive closure of all the overlapped spines. Then, for conjunction like this, we can generate is a P-star graph like this. This graph is very important because each path in this graph represents a truth assignment and which the corresponding conjunction evaluates to true. For example, when we go along this path, starting from this node, then this node, then this node, then along this edge to the end node, we just get a truth assignment and which the corresponding conjunction evaluates to true. Now we can search another path in the graph, we'll find another truth assignment and which the corresponding conjunction evaluates to true. For example, if we just go from this node, then this node, then this node, then along this spine to this node, then along this spine to the end node, we just get another truth assignment and which the corresponding conjunction evaluates to true. Now, what we want is to merge all the P-star graphs for all the conjunctions together to generate a trine-like graph. In the first step, we'll generate the trine structure of all the main paths in all the P-star graphs. For example, for the above example, we can generate a trine structure like this. In this trine, each path, in fact, is just the the main path in a P-star graph constructed for a certain conjunction. For example, this path, in fact, is just the main path in the P-star graph constructed for the conjunction D1. Then this path is the main path in the P-star graph constructed for the conjunction D4. And this path is the main path in the P-star graph constructed for the conjunction D6. Then I just put all the transitive closure in all the P-star graph to this tri-structure to generate a trine-like graph like this. Here, special attention should be paid to the number associated with the spline. For example, the number 4 associated with this spline just indicates that this spline belongs to the P-star graph constructed for conjunction D4. And the numbers 2, 3, 4 associated with this spline just indicates that this spline belongs to 3 P-star graphs constructed for 3 conjunctions, D2, D3, and D4 respectively. Then I search the trine-like graph budding up to generate its layered representation. First, we just recognize all the leaf nodes to make up the first label. Here is the first label. Then we'll find the parents of all the nodes at this label to make the second label. At this label, we'll categorize all the nodes in different groups, such that each group contains all those nodes with the same label, or say, with the same variable names. For example, these 3 nodes are labeled with the same variable names. Then all these 3 nodes will be put in one group. Then these 2 nodes are labeled with the same variable name C2. Then these 2 nodes will put in another group. All the remaining nodes are differently labeled. Then they are not continually explored. Then in the next step, we just try to find the parents of all the nodes in each group. Again, the nodes at this level will be categorized into different groups. We just continue this process until we meet the level such that all the nodes at this level are differently labeled. This layered representation of the graph is quite useful because by using this graph, the solution to our problem can be found very efficiently. For this purpose, we'll recognize all those nodes which does not have a parent. Then we call each of such nodes a root, and each root recognize a subgraph which contains all those nodes. Each of them is reachable from the corresponding root. For example, these 5 nodes make up a rooted subgraph, and then these 4 nodes make another rooted subgraph. Each rooted subgraph identifies a subset of conjunctions which can be satisfied by same truth assignment, as shown on this slide. You can see by this noted subgraph, we just identify a subset which contains two conjunctions, D2 and D4, which can be satisfied by a truth assignment represented by this set of variables. That is, any variable in this set will have value equal to 1, while all the other variables not appearing in this set will have value equal to 0. We just take another example. By this example, by this noted subgraph, we just identify another subset of conjunctions, which can be satisfied by a same truth assignment represented by this set of variables. This working process can be greatly improved. It is because in this process, a lot of lots will be repeatedly accessed. For example, this part of the graph is completely identical to this part of the graph. Then any nodes in this graph should not be explored. In this way, we can have a polynomial time algorithm to find the solution to the two-mass-sort problem. In summary, in this talk, we have presented a very efficient algorithm to solve the two-mass-sort problem. For this, a lot of important and interesting concepts have been discussed in great detail. They are p-graphs, p-star graphs, and triangle graphs. Then by searching a triangle graph bottom up will generate its layout representation. By using this layout representation, we can solve the two-mass problem very efficiently just in the polynomial time. Because the two-mass sort problem is NP complete, then our algorithm discussed in this talk is in fact a proof of NP equal to P. Okay, that is all for this talk. Thank you for your attention.